Saxon Advanced Mathematics, Lesson 5. Greetings to my students. It was wonderful to video chat with each of you last week. It all worked out perfectly. That's what we're going to do every Friday. I don't think that I checked everybody's lesson checklist to make sure that their parent had signed off on it. Each of you also have a sibling working with me, so you can always, if your mom's busy or your folks are out of town or some crazy thing, you can always check each other's work too. I'm completely fine with that. So please make sure that you have signatures for anything done that you're ready to have signed off. Obviously, if you're not done yet, don't sign it off, but get those signed off and show me as soon as possible. Based on everyone's availability, I'm changing my office hours slightly. I'm going to have some availability on Thursdays from noon to 2 for the weekly video chats, and then I'm going to keep my Friday hours. I'm going to try noon to 2. Vivian and Laura, I think I talked to you slightly after 2, but you told me next time it would be sooner, a little earlier. So let me know if that works for you, and we'll fine tune this. I just want to make sure I'm getting time. There's too many students who have busy Fridays and asked me if I could provide some options for them on Thursdays. So that's what I'm doing. All right, so we'll keep working on that, but you guys handled it perfectly last time. Yay. All right. We're going to talk about exponents and radicals. Yay, we're going to start doing a little bit more algebra, which I'm excited about. So what I want to do first is review our rules for exponents. If you've been with me before, you know I love this chart and I draw it all the time. It's not something that John really summarizes this way, but I do. So work with me. This chart I always draw the same way. There are 3 rules for exponents. One is called the product rule. One is called the quotient rule. And one is called the power rule. I'll let you catch up with me on that much before I show you how these rules work. You already know them. I know you know them. I'm just writing it down in this organizer that I use. When I was in algebra, nobody ever wrote this down and showed it to me so I could compare them, and it drove me crazy. I recommend that you put this in your formula notes on the inside of your cover and commit it to memory. It is a lifesaver. All right, the product rule deals with situations where we are multiplying matching bases, right? X and X, they have to match, and each of them have an exponent. In that case, we can simplify by simply adding together the exponents. The product rule refers to the fact that we are multiplying here, but the way we combine the exponents is to add, okay? That's rule number 1. The quotient rule deals with situations where we are dividing, right? Quotient is a dividing rule, a dividing word. This signifies dividing. In these, again, matching bases, we subtract the exponent in the numerator minus the exponent in the denominator, okay? And then the power rule involves the situation where we have a base being raised to a power and we want to raise it to an even higher power, okay? That's what this is describing. And in this case, we multiply the exponents. We're going to do this. We're going to use some fractional exponents just to make it, super delicious. Nothing changes. Our rules work exactly the same. We just deal with fractions instead of whole numbers, as we are used to doing. So I'm going to flip the page, but make sure you have this copied. Pause me right now if you'd like and copy this into your notes so that, or not your notes rather, but your cover, right? Front or back, wherever you've got your notes, your formulas organized. Do that so you've got it. I'm going to flip, meet you on the other side. Okay, So let's put this little pup in action, but first we're gonna make it extra messy because we're going to write these in radicals. So our first step is we want to get rid of these radical signs and have everybody with an exponent. And if that means fractional exponents, so be it, Jedi. We're not afraid of them. So remember that the way that we do that is, first of all, we look to see what root we're taking. Now this doesn't have a number out here, so we know that's a root of 2, a square root. So the way we do this is we take the base and exponent information from the inside, we put that in parentheses, and then we change that root sign into a fraction with that number on the bottom. That's tricky. Okay, we'll do the same thing over here. We create parentheses, we put the contents, I call those pig houses. I think it's only fair to let all of you know. We put the contents of the pig house into a set of parentheses. I'll explain later why it has to do with 3 little pigs. And then this, the root sign, this is a 4th root, that becomes the number on the bottom of the fraction on the outside. Okay, so that's how we convert radicals into fractional exponents. Yay. Now we have a situation where we need to apply the power rule, don't we? Because we're taking numbers that are being raised to, or not, well, they're numbers technically, but they're quantities is the better way to say it. We have this quantity, we want to raise it to this power. We've actually got 2, but this one doesn't have an exponent on it, so I'm going to give it 1 so I don't get confused. I'm going to put those 1s in. We can always say we're raising something to the 1 power. So now our power rule tells us that when we want to apply this, when we want to simplify, we're going to multiply that outside exponent times the inside. And again, the fact that it's a fraction doesn't change anything. It just makes our multiplication kookier. Okay, so 1/2 times 3 means that's x to the 3/2. Notice how I'm exaggerating and giving myself a ton of space and making that 3/2, and make sure it goes up high enough so that it doesn't look like it's just another base. That's an exponent. And then this one, y to the 1 power times 1/2. Okay, so that's the first one. Now this is all being multiplied, so I don't need any kind of sign in there. I'll just write them in a row. X, 1 times 1/4, and y, 3 times 1/4. Okay, so this is the power rule that we used to get rid of the exponents on the outside. And now we're ready to use the product rule because we've got multiple bases that match, right? There's 2 x's. So what I'm going to do is I'm going to simplify this presentation. I'm going to look at the x bases first, and I've got 3/2 plus 1/4. I need to add them, right? That's what the product rule tells us, is that when you're multiplying bases, you add the exponents. I need to fix this so I can have matching denominators. This will be 6/4. Now I can add them. It's 7/4. So the exponent, the simplified value of the exponent on the x term is 7/4. Cool, let's do the y. 1/2. And we're going to add 3/4, right? That's how the product rule works. This will become 2/4. And then the final exponent will be 5/4. So my final answer is x to the 7/4, y to the 5/4. And I think that is way cuter than that, right? That was fun, kind of cool. All right, that's 1. How many? This is kind of a long lesson, you guys. I gotta break it to you right now. It's kind of long, and it's kind of crazy. I just got a low power mode message on my phone. So this could end up being broken into two. Sometimes you guys, I try to tape them all as one big lesson, but sometimes things happen and I have to do you a part 1 and a part 2. Sorry. Sorry ahead of time for when that happens. I do put my phone on airplane mode so I don't get somebody calling me and making me cry. All right. This one, are you ready? Copy this and try not to cry. Right? Look at all that nonsense, right? We have to deal with it. Okay. The first thing we're going to do is simplify. Let's see. We'll simplify using the product rule. We have to do it like that because there's 2 terms in the exponent, so we have to multiply both of them. And then we're going to bring these guys up to the top so that everything's in the numerator. All right, so we're going to use not only the power rule, but also the quotient rule, kind of at the same time, and it'll be fine. All right, so a to the x over 2, he's the same. Then we'll have y, let's see, 2, this 2 times 1/2 is 2 over 2 or 1, minus x over 2. See how I got that one? X times 1/2 would be x over 2. All right, then let's bring this a up, so that will become a to the minus 3x. Right, because we're subtracting it, or you can think of it as a negative exponent. Either way, we're bringing it up to the numerator, or you can think of it as we're subtracting it. We'll get to that in a minute. And then we need to bring this one up. Okay, this one's going to go positive on us, isn't it? It's going to be plus 2x. Okay, notice that negative exponents and the quotient rule for exponents do the same thing. They are complementary rules that don't contradict each other, which is a big yay, right? All right, so now we've got everybody in the numerator. We've got everything as simplified as we can using these 2 rules. Now we're ready to use the product rule. Okay, so for a, we're going to take x over 2 and we're going to add a negative or subtract 3x over 1. Okay, this has to be multiplied by 2 over 2 so that we get matching denominators. So that's 6x over 2. So now I'm just crossing that out so that I can see this is what I'm actually subtracting. X minus 6x equals minus 5x. Denominator stays the same. Yikes, that was a lot, right? And now the y's will do the same thing. We've got 1 minus x over 2 plus 2x. In order to combine that, we have to give everybody matching denominators. So this will become 2 over 2. And this will become, let's just write it here, 4x over 2. All right, so now everybody's got matching denominators. 2 minus x, can't do anything with that. Plus 4x, that would be 2 plus 3x, right? Minus 1 plus 4. 2 plus 3x, and then denominators over 2. So our final answer is a to the minus 5x over 2 power, and y to the 2 plus 3x over 2 power. And if that doesn't make you feel smart, I don't know what will, you guys, because that's freaking amazing. Even if you just followed it, even if you're sitting there thinking, what just happened? I think a truck hit me. You rocked it. You absolutely killed it. It was great. Okay, flipping. 5x plus, or example 5.3, sorry, I'm turning everything into a problem. Ready? Simplify. X to the minus 2 plus y to the minus 2. Okay. This one's a little bit tricky because this notation, it has a trick buried in it. We can't just flip these down because of this plus sign. If we were multiplying, we could, or we could bring this up, but this creates problems because the way we simplify this is 1 over x squared plus 1 over y squared over, and then let's do the same to this one, just so that we don't make ourselves completely crazy. All right, so what we've created here is kind of a complex fraction problem. This forced us to do this up here, and then once we did that, we realized, okay, let's just do the same thing down here and treat it all as one big, we already created a complex fraction, so what's the harm in one more? All right, in order to simplify this, we have to use our complex fraction skills. These, I always like to start at the bottom, so I don't want to talk about those first. In order to turn this denominator into a 1, we need to multiply it by xy over 1. That creates a reciprocal situation where we have xy over xy. It all turns to 1, it goes away. We can ignore it. One in a denominator can be ignored quite nicely. This, we're going to have to work on to get these to match, but we're also going to need to multiply it by xy over 1, because if we did it to the bottom, we have to do it to the top. Yay! Okay. We're getting somewhere, you guys. We've got it down to just this. Now, these denominators have to match. The least common multiple, or least common denominator, is going to be x squared, y squared. Oh wait, no, I don't want to do that. I want to do top and bottom. So this is going to be y squared over y squared, and this is going to be x squared over x squared. So this is all going to turn into y squared plus x squared over x squared, y squared. I don't want to use the least common multiple scenario because that only works when I have an equation. I'm not dealing with an equation here. I've got an expression. There's no equal signs in sight. So I have to use numerator, denominator, same quantity rule rather than multiplying every term. All right, so this turned into this, and we have to multiply it by xy over 1. This will cancel, won't it? There's no addition down here to keep me from not doing that. So I can cancel one of these x's and one of these y's. So my final answer is going to be y squared plus x squared over xy. La 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 la. When I look, yay, that's the right answer. But when I look at the book, John's answer, I say, whoa, he wrote x squared plus y squared over xy. I wrote it the other way around. But guess what? Addition doesn't have an order to it, right? X squared plus y squared is the same as y squared plus x squared. So no biggie. Done. Example 5.4. Let's deal with some radicals now. Copying. Here's my metaphor for dealing with radicals. Radicals are like 3 little pig houses. You know the story of the 3 little pigs. They each built their own houses, and then the wolf started attacking, and they had to run from house to house and cluster together, and then eventually they ganged up, came out of their house, and made mincemeat out of the big bad wolf. Various stories. Sometimes he comes down the chimney, but in our story, the pig comes out. The pigs come out. So, numbers on the outside of the radical sign are the wolves. Numbers on the inside are the pigs. Okay, we'll break this metaphor down as we go. In this case, we've got fractional pigs. And you know what? We're not really down with that. We would much rather break them out into condos, right? So they can live separately. So this is how we're going to change this problem without really doing anything. Okay, so I just rewrote this by taking the fractions out. I split those pigs out and I gave them condos so they don't have to share an upper or lower floor in the same house, all right? Now, as you look at this, you see radicals in the denominator, and I hope you're cringing. I hope you're just so uncomfortable and kind of skeezed out by that, because we mathematicians hate that. We hate having radicals in the denominator. So what we do is we rationalize them. We rationalize the denominators, and these are cute little denominators. The easiest way to do it is to multiply top and bottom by whatever's on the bottom, because that's going to make a plain old 2, right? And this one I'll do 3 over 3. We are dealing with expressions rather than equations, so we use that up and down, numerator, denominator, same quantity rule. We're kind of ignoring him. We'll deal with him later. So now we've got 3. Remember, when we multiply wolves to wolves and pigs to pigs. This is a multiplication. So we have a 3 wolf, and then we have a 6 of pigs, right? The 3 and the 2 pigs multiply. On the top, 2 times 2, we have, you can think of it as square root of 4, or you can think of it as whenever you have 2 pigs together, they can jump out, okay? So either way, that's the same as the square root of 4. That gives us a denominator of 2. Minus, here we go, wolf to wolf, pig to pig, 4 square root of 6 over 3, right? 2 pigs jump out. Plus, I think it's about time we broke this down. I think we're all convinced that we could fix this. 24, right? In order to simplify this, we break it down into some factors. 24, I know, is 8 times 3. So I know it's going to be 2 times 2 times 2, because 8 is 2 cubed, and then a 3. So here's a pair of pigs that we can take out. So we're going to multiply 1, 2 against this wolf. So that'll be 4 on the outside. And then that's going to leave us these 2 pigs left inside. So that's 6. All right, look what we've done. We've got some pretty cool matching radicals there, right? And these are kind of like variables. They behave kind of like variables because we can't do anything to combine them unless they match. But they do match, so yay, we're happy. That 6 is nice. Unfortunately, we still have a denominator issue because we have unmatching denominators. So even though the radicals match, we have to make the fractions match before we can actually combine them. Oh, such drama. So we're going to figure out what's our least common multiple. That is going to be 6, right? So this one has to be multiplied by 3 over 3. This one has to be multiplied by 2 over 2. Put the dot in there. This one has to be multiplied by 6 over 6. These are all on the outside, so they're wolves. So now let's do this. 9 square root of 6 over 6 minus 8 square root of 6 over 6. Sorry, my lines have gone completely off the rails. And then this one, 24 square root of 6 over 6. Yay, we did it. We made them all look cute and matchy. And now all we have to do is combine. We only have to pay attention to these numbers now, right? We made everything else match. 9 minus 8 is 1 plus 24. Our final answer is 25 square root of 6 over 6. We can't reduce 25 and 6. We can't break this down anymore. So that is the end of our happy tale. Oh my gosh. That was exciting, wasn't it? Quite. Flipping. Now we're going to practice a multiplication. Example 5.5 with radicals. Let me just show it to you. It's binomials. 2 binomials we're multiplying. All right, we know how to do that. And there are radicals in there. All right, well, we can handle that, right? That's not a big deal. Some of my students may be used to using the FOIL method. If you do, that's cool. Go right ahead and use that. I don't use that. I use what's called the vertical or the stacking style of multiplication like John does. So I will do it that way. If you are committed to FOIL, go for it. But I'm going to continue with this. All right, so what we're multiplying, I'm going to copy them without the parentheses because I don't need them in this format. Remember, when we're multiplying binomials, we write them on top of each other. If they're not the same size, we left justify. With basic multiplication, we right justify, but with binomials and algebra, we left justify. And I tell this as a story of some kids at a dance, an old school dance where the boys sat on one wall and the girls sat on the other wall and everyone was scared to ask. But these are the boys, these are the girls. This girl is brave. She gets up and first she asks this guy to dance. 1 times the square root of 2 is the square root of 2. When they dance, they multiply. That sounds weird, but it's fine. Then she dances with this guy. 1 times the square root of x, square root of x. Sign stays the same. She sits down. She's done dancing. Now this girl gets up. She's more complicated, right? Her friend's just +1. That's basic. But she's a complicated woman. She's a minus square root of x. So we're going to have to deal with her. She multiplies with him. She dances with the same guys in the same order. This becomes minus, let me write it over here more, minus square root pig times pig minus 2x. And then she dances with this guy, and that becomes, let's just write it this way, minus square root, it's x squared, right? X times x is not 2x. X times x is x squared. All right, so let's see what we've got here. Let's see if we can simplify anything. Square root of 2, that's clean, plus square root of x. Can't simplify that. But this we can simplify because the square root of x squared is x. So we can just write minus x. Oh, that's complicated. All right, this is the answer that I like and I would want to see. John says, hey, let's factor the square root of x out of that. I don't want to do that. This is the step before his final answer. This is the answer I want to see. What he's doing in his factoring is too complicated for where we're at. All right, so just skip that for now. All right, moving on. That was only part A. Come on. That is so much. Complex numbers. Remember that complex numbers arrive when we have minus signs inside radicals. Okay, so when we have a minus sign inside of an even numbered root, this is the invisible 2, right? That causes us a lot of drama. That's not a number you can find in the number line. So we call it an imaginary number. And we write it like this, right? And so we say our definitions are, if you want to find the square root of -1, it's I. And for every 2 i's you have, that's just a regular -1. So these are our definitions. Hopefully you remember that a little bit from last year. Let's look at the problems and see what John wants us to do about this. 5.6, ready? Simplify. 3 sort of trespassed there, sorry. Remember that every pair of eyes turns into a -1. Pair of letter eyes, not eyeballs in your head. So we can, if you want to, you can write these out, right? I cubed means there's 3 eyes. 2 of them changes the sign on this, so it becomes -3, then we have 1 left over, right? 5 of them, these 2 become a -1, these 2 become a -1, so that means they become a +1. So this stays positive, and then we just have 1 I left over. -3i, we can't simplify that. And then this one we can simplify again because these two i's go together to make that a -2, and that uses them all up. So what we are left with is what we call a complex number, because we have one number without an I, and then we have a value. All of these guys can be combined, right? It's -6 plus 2, that would be -4. Checking to see if my answer is right. Yes. Okay. This is called a complex number. It's always in the form a plus bi, in which a is the real number and b is the imaginary number. And together they're called a complex number because it's got a real and an imaginary part. We can write anything as a complex number because let's say we pick the number 101, right? 101 Dalmatians, that's pretty darn real. We can say it's, if we want to write that as a complex number, we can say it's 101 plus 0i. Okay, so every number can be written as a complex number. You can just stick 0 in there if you want. All right. One more problem in this area. Example 5.7. Simplify. Okay, so we've got a lot of frightening looking things here, and we're just going to break it down and go through, and we remember that anytime we have a negative sign, we can swap that out for a y. So this becomes square root of 3i, right? The square root of 3 is untarnished. It's just the -1 that we pull out. Times the square root of 4, well, that's 2, right? So why don't we just fix that right away? I'm going to put this in parentheses, and then I'm going to put 2 in parentheses, so I see that's multiplication, just like there. Plus, okay, ready? We'll do the same thing here. It'll be 3 times square root of 2i times square root of 9i plus square root of 16i plus square root of 16. I stopped simplifying halfway through. There was too much going on, right? So I simplified that square root of 4 into a 2, and the other ones I just left. All right, so this will become 2 is the wolf, square root of 3 is the pig, I. We're multiplying all that. Okay, these 2 i's come together to make a negative, so that's going to become negative, and then we've got 3, and we've got square root of 2, and then this will be 3. So it'll be minus 9 square root of 2. And I'm just going to get rid of that plus sign that I copied because these 2 i's turned me negative there. All right, plus 4i plus 4. Okay, so we've simplified each of those terms down. Now we want to get it into our complex number format. We want to combine all the real numbers, which is this and this, but they don't really combine because this is square root of 2 and this one isn't. So we write 4 minus 9 square root of 2. That would be the way I would present it because 4 is an integer and this is an irrational number. So I would write it in that order. And then plus 4 plus 2 square root of 3i. See how I kind of like factored those two numbers and wrote them as the I? That is the best, and I'd put parentheses around this. This is the closest to a plus bi format that we can get for our answer. That's a kooky looking answer, right? Okay, that's enough complex numbers for today. I've got them into your brain and going crazy. So that's enough for now. I'm gonna pause this lesson right now and do a part 2 to finish off the last couple topics. I think this is a good place to stop and try a few problems to see if you've captured this in your brain, and then we're gonna switch to geometry. So I will do that in part 2. Thanks. See you on part 2.